add the two expressions. Actually, I guess 3. So that's worth 2 points. And then getting it separated into the part that didn't multiply alpha wing body and the part that did, that was worth 2 points. And then clearly identifying which was what was worth 2 points. Okay, problem 2. What is static margin? It's the Kn thing. The formula wouldn't cut it. You have to define it. It's the distance from the CG to the neutral point in fractions of C bar. So getting the correct points that we're distancing are 2 points. You had to say C bar, so that was worth 2 points. And the calculation. You have to calculate H was 10 over 5 because it's in fractions of chord. That was worth 2 points. Using the right formula was worth 2 points. And then calculating Hn times C bar was worth 2 points. And then you have to draw it on the airplane. And I didn't intend for you to do this, but if you shortcutted the process and calculated this by simply taking 0.35 times C bar, I think you got like 1.75. And if you drew that on the airplane and located the neutral point relative to the CG, I should have given you full credit. If I didn't catch that when I was going through there, make sure you see me. Following what I'm saying, you had to do this. You had to show the calculation in feet and draw it on the airplane and then say the stability was based on that. Most people did it this way, if you did it right. And then the answer to the final question is yes. And it's just totally based on the fact that the static margin I gave you was positive. If you calculated the neutral point, or the neutral point and showed that it was aft and you said that was the case, I gave you credit. If you got the neutral point wrong and it ended up forward and you answered the question incorrectly, I did not give you credit. Because you didn't need to calculate the neutral point. All you needed to know is the definition of static margin. Let's see, so I gave you the points, right? So make sure that I added up correctly and that I gave you all the points that you deserve. And I'll be available on Monday before class if you want to come by and talk to me about your quiz. And I'm usually here. I know a lot of you guys have structures. I'm typically here by 8:45, 9 o'clock. So if you want to come before you go to structures, that's good. Okay, so we were talking maneuvering flight last time, right? So we were doing a pull-up. And we had calculated Q hat, the non-dimensional pitch rate. where we had defined the weight coefficient and the mass ratio mu. So I gave you the formulas for that. And so where we ended was that we had two equations for level flight, and then two equations for the pull-up. So for level flight, pitch trim, CW is CL trim. And then pitch trim equation is the pitching moment is 0. And then, of course, we have a third equation for the hinge moment, but we don't need that right now. So this is for level flight, and remember, we're dropping writing the trim on all of these just because we're going to know that this is the trim condition. So we're not writing trim, but it is the trim condition. And then we say for the pull-up, the total lift is the load factor times the weight coefficient, because lift equals N times weight. And for that, we're going to be flying at an extra angle of attack delta alpha above and beyond what we're using for level flight. So again, we're comparing the pull-up to level flight. Here's trim for level flight. We're saying we're going to trim at an angle of attack that has extra delta alpha. So let's erase the trim thing there. And we're going to have some extra elevator. But remember, we're not changing the trim tab because the pilot won't do that just for a quick maneuver. He'll just do it with the stick and leave the trim tab alone. So don't change the trim tab. And then we have to add in, oh, it didn't leave me room. I got to add another term on here. We got to add the effect of the pitch rate, Q, on the lift. And this is where we use that Q hat, the non-dimensional pitch rate, to add in there. So let me rewrite this. Don't change delta T during pull-up. And I'm going to talk about that in a minute. I'm going to draw a picture, but let's just write it there. We're going to say the lift changes, and then the pitching moment is going to change. We still want it trimmed in the pull-up. We still need 0 pitching moment. But this is going to happen at the new angle of attack that gives us the pull-up. And the new elevator. Again, we didn't change the trim tab, so we're good there. But the pitching moment can change due to the pitch rate. So we'll add that in there. All right, so I want to draw a picture explaining why, if the airplane's rotating, we are going to get a change in the lift and the pitching moment. So here's our wing, here's our center of gravity. So the airplane rotates with a pitch rate, that's positive pitch rate, about the CG, and then here's our tail back here. And this is LT. So if the airplane's rotating, this thing is moving downward at a velocity of q times LT. So the moment arm times the angular velocity. So that creates an additional upward component of the flow. And so we're going to get extra lift. And that's what that represents. And then because we get extra lift here, we're going to get a downward pitching moment due to Q. It's not due to anything else. It's due to the fact that the tail's moving downward. And so we get that extra lift upward. So we get a pitching moment due to the pitch rate. Now the wing is rotating, but most of the time the CG is pretty close to the aerodynamic center. There is a little bit of an effect of this thing rotating, right? Our center of lift of the wing is here. And so because the wing is rotating, we do get a little lift change and pitching moment, and it's just all added into those terms there. So you have to take your airplane, and if you really want to do it right, you go into a wind tunnel that has a rotary balance where they actually rotate your wind tunnel model and can measure these parameters. All right, so we're saying we already know alpha trim and elevator trim and the trim tab, because we know how to do that already. So we want to get delta alpha and delta delta E. So we're going to subtract. We're going to subtract the top set from the bottom set, and that's going to give us equations that we can solve for the extra elevator and angle of attack. Sorry, were you guys done with this board? Are we good? So if we have subtract, let's switch back over to the other board real quick. What are we going to get? So we're subtracting the top lift equation from this one. So you can see that this term is going to cancel that term out, right? And then the CL delta E gets subtracted from this, so that term is going to be gone. And then the trim tab, we didn't change the trim tab, so that whole term gets subtracted out. And we're left with the angle of attack and the elevator change, and then the pitch rate, which we're going to get from our formula here. And the same thing for the pitching moment. The alpha term gets out, so does the elevator term and the trim tab term. And so we'll be left with two equations for two unknowns that we can solve. So when we subtract the CW from NCW, we get N minus 1 CW. And then I'm going to stick in for Q hat, our formula that we derived for that. So that thing is Q hat. So we can say, okay, I'm doing a 3G pull-up, put in 3 for N. I know my CW, I know my mass ratio, and that term we know. And then 0 minus 0 is 0. We get Cm alpha. And so this allows us to solve for the extra angle of attack and the extra elevator that we need. If we want to know the total angle of attack, we just add the delta alpha to alpha, and that's the angle of attack we're flying at the pull-up. Same thing with the elevator. The reason that he solves for delta E is because we want to calculate how much extra elevator it takes to do a pull-up, because that's extra feedback, important feedback to the pilot. If we just wanted to find out how much elevator total we needed, we could, of course, just solve for the bottom 2 equations for the 2 unknowns, and we're good. But we're going to take each equation and divide by n minus 1. And then that gives us the extra elevator per extra G, right? Load factor of 1 is level flight, so n minus 1 is the extra load factor that we get due to the pull-up. Like if we're flying a 3G pull-up, level flight's 1, so we get 2 extra Gs. Sounds kind of weird, doesn't it? And then we're dividing this by n minus 1. So that's the reason that he formulates it like this in the book. So if you're taking notes just right, then we divide both equations by n minus 1. And so what we have is we solve for the extra elevator per G and the extra angle of attack per G. And that's what we want to know. How much does the pilot have to pull on the stick to do a pull-up? Because the stick's connected to the elevator, and in fact, we're going to calculate how much stick force he has to generate to cause this extra elevator deflection that causes the pull-up. So we'll put this in a matrix because that's just the easiest way to do this. So we'll have, these are our 2 unknowns. Take this equation and pop it over into a matrix. Checking the time, 11:13, we're good. And how does this change from the 2x2 trim problem we had for level flight? CW is over here, that's what we had before, but we've got these extra effects due to the pitch rate that are happening during the pull-up. So if we use Kramer's rule, I always draw a blank. Is it K or C? C, isn't it? Somebody look it up. Google it. You can do Kramer's rule. It's the ratio of the determinants. And this is in your book. This is equation 3.6-6, equation A. And then equation B is for delta alpha. Same old determinant that we used before because it's the determinant of that same matrix. Because of the motion of the aircraft's diving down, and you're doing this kind of maneuver, you're pulling the nose up on the airplane. We want to pull on the stick. It turns out it's natural for the pilot to do this during the pull-up. Just makes sense. He's pulling the airplane up, right? So for good pilot feedback, just like in your car, it makes sense to turn the steering wheel to the right to turn to the right, right? Makes sense on a bicycle to turn the handlebars to the right to go to the right. Same deal here. They used to have a bicycle at a carnival we went to in Andover. If you were able to ride this bicycle, you won an iPhone. Actually, back then it was an iPod. That was cool. But they had geared the bicycle so that you actually turned it the opposite direction. To turn right, you went left. We all learned to ride bicycles to balance by turning, right? It's in your brain. And so it's impossible to ride. The guy that ran the booth could ride it because he had practiced and he made it look easy. But then you got on it and there's no way because it's geared backwards. So for good pilot feedback, this is natural to the pilot. We want that. And so if you pull on the stick, which way does the elevator go? Here's our horizontal tail. Here's our CG. We always got to connect this. We're talking about moving the stick back that way. And that's going to pitch the nose up, right? So what kind of elevator motion is going to pitch the nose up? And this is how we have to connect it, because you can connect the stick to the elevator however you want, but in airplanes it's connected so that when you pull on the stick, the nose comes up. So to pitch nose up, we need an elevator that way, right? It's going to push the tail down and the nose is going to come up. So this is negative elevator. So we want the change in elevator per G to be negative, so that the pilot has to pull on the stick to get the pull up to happen. And again, that's another reason why that makes sense, is the gearing is to pull the nose up. You pull on the stick to pull the nose up. During the pull up, the nose is coming up, so it all connects together. So will this thing be negative? Are we close to time? 1 minute. So we'll stop after this. Here's a negative sign. Cm alpha, if we're stable, is going to be negative, right? So that looks like it's going to make it positive. Minus a minus, but we've got a minus here, so that's going to be change. Once we've built our airplane and we got good feedback, what could possibly change? It's the same old thing that changes with just normal pitch stability. Cm alpha may change. And so we need to look at the effect of CG position on Cm alpha and the effect of CG position on elevator per G. So we'll do that next time. There's new homework posted for next week. You can get started on that. It's calculating this